In this video, I want to quickly summarize the methods that we've learned for finding roots of functions and to optimize functions. And there is one thing that all of these methods share, which is these are all iterative methods where you first have some kind of initial value, and then you take one step. And then that becomes your new value, and then you take another step from that point. And then you keep taking steps until you've reached your answer. So intuitively, they're kind of all the same. So the main thing that you have to remember is how to take a step for each of the methods. So let's start with the different root finding methods, starting with bisection. So here I'm always going to start with an interval. Let's say that I start with an interval between xl and xr. Maybe I can use a different color to make this a bit more obvious. But okay, so I always start with an interval such that if I evaluate my function at my left and at my right, when I multiply them, they are negative. So what that means is that one of the two is positive and the other one is negative. And then I'm just going to go to the middle of the interval. And I ask myself, is the root that I want to find to the left or to the right of this middle line? So let this be xn. And pretend, of course, that this is exactly in the middle between these two numbers. So I know that there will always be a root if in an interval one of the values is positive and the other one is negative if this function is continuous, right? Because at some point this function has to cross 0. So here I see that both values are negative. So instead I continue with this right interval where one is positive and one is negative. And again, in this interval, I'm going to draw a new middle line. And then within these new two intervals, I'm going to check whether my root is to the left or to the right. So here I see that both of these values are negative, but here there's one positive and one negative. So the root has to be in this new interval. And again, I'm going to cut the interval in half and evaluate my function at the middle. And I ask myself, is my root within this interval or in this interval? And in this case, it's going to be here because this is negative and this is positive. And I continue doing so until my interval is small enough. So usually we have some kind of tolerance, and when the interval is smaller than that tolerance, I'm just going to take the middle of that interval and say that's approximately where my root is. In the second method, the fixed point method, I'm converting this problem of finding a root of f into another problem, namely finding a fixed point for the function g. So instead of f(x) is 0, I can rewrite this function as g of x is x. And then how to take one point? Well, I simply evaluate my old point in g, and then that whatever comes out of there is going to be a new point. And then I'm going to evaluate g at this point, and then whatever comes out of there is going to be my new point, and I keep going until my x no longer changes, basically, or until until some kind of maximum number of steps is reached. So for a lot of these methods, it's not guaranteed that you will converge. So you might diverge and move further and further away from the root that you want to find. In that case, we usually have some kind of counter so that if a maximum number of steps is reached, say 1,000, we simply stop the algorithm. So in the Newton-Raphson method, yes. So here, if this is my old x, my new x is simply going to be my old x minus the function evaluated at my old x divided by the derivative evaluated at my old x. So here, assume that this point was my old x. What I basically do is, so assume that the function continued in the same way after this point. So the function actually deviates a bit, but if it continued in the same line, a straight line, then here I would expect a root, right? So I'm basically going to take this as my new x, and I can find this by, of course, using this function here. And finally, in the secant method, so what if I don't have the derivative of f, right? So I might not know the function that codes the derivative here. In that case, I can approximate the derivative by looking at 2 points, right? So instead of 1 point, now I have to keep track of 2 points. And this function basically gives you what the next point is. And for the next iteration, x2 becomes the new x1, and x1 becomes the new x0. And then I can again apply this method to find a new x2, and I continue until I converge somewhere. Okay, so when looking at optimization, maybe it's easiest if I first mention this. So of course, for a local optimum, what I know for a univariate function is that the derivative at that local optimum is going to be 0. So I could basically just use this method to find a root of the derivative, right? So I want to find an x such that the derivative evaluated there is 0. So here, my function is no longer going to be f, but just the derivative of f. Yeah, so instead of xn here, you can always see this as x old. Maybe it's useful if I'm consistent here. Then this is going to be my x. So here I'm basically just using this function, except that my function is going to be the derivative of f instead of f. And of course, then my second derivative I'm going to use instead of this first derivative here. This is exactly the same method as here. In the golden section method, what's the best way to illustrate this? Maybe let's find some graph here. Let's say this one. So in the golden section method, I also always start with a segment or an interval instead of a single point. So let's say that I start with this interval here. I have an XL here. I have, say, an XR here, and then some kind of XM. So here in the middle, there is an XM. And what's important for the golden section method is that the function at XM is going to be higher than my function at XR and XL. So once I have these 3 points, I can calculate a y here somewhere. So somewhere in the interval, in one of the 2 intervals that is wider, and there is a function to find this y given these 3 numbers. And then I simply ask myself, what are going to be my XL, XM, and XR for the next steps? It's either going to be these 3 or these 3, but I keep in mind that my XM has to be higher than the other 2 points, right? So if I took these 3 points, obviously my XM would be lower than this point. So I have to continue with these 3 points, right? So in my second iteration, let's see if I have a different color here. So in my second iteration, I'm going to use these 3 numbers, and then this y is going to be my new XL, this middle point is going to be my XM, and this right point is going to be my XR. Right, so and then within here, I will be able to calculate a new y. I evaluate the function at this y, and again, I have to choose either these 3 or these 3 points to continue, and I always make sure that the function evaluated at the middle point is higher than the function evaluated at the other 2 points. And if I continue to do so, at some point, I will converge to this local optimum here. So for the univariate case, we've seen these 2 methods. to optimize the function. And then if I have a multivariate case, I can either use the Newton's method here. This is basically the same as this Newton's method, except that I've extended it to multiple variables, right? So instead of this derivative of f, I have the gradient evaluated at this x old, where again here the xn is no longer going to be a single point, but it's going to be a vector. And then instead of dividing by the second derivative here, I'm multiplying by the inverse of the Hessian. In the steepest ascent, I don't need this Hessian information. Instead, to go from my old to my new point, I simply take a step in the direction of the gradient. So this gradient tells me in which direction the graph is the steepest. And how far I take this step is given by alpha. And there are different ways to find this alpha. So usually we use some kind of line search to find the alpha that finds a local optimum in that direction. Because of course, once I've decided on this direction, this whole function would be a function of alpha, right? So I could take a small alpha, then I move a tiny bit in that direction, or a large alpha, and I move a lot in that direction. So then I could use, for example, this golden section method to find an alpha, so the best step size that gives me the function that kind of gives me the function that is the lowest at that point. So maybe that's not entirely clear. But basically, so assume that here in this is the graph of my function. So assume that this was my old x. So if I know that I have to move in this direction and this graph moves like something like this, what the line search is going to do is basically use some kind of optimization method so that I know that I end up at this point, right? Where in this direction I have different values of alpha. Okay, so now that we have this intuition, I also want to show graphically basically what is happening if you did this in R, in case you want to see it here. So I've plotted the function f, and we can see that the function f is simply x squared minus 4 here. And the derivative of f is then, of course, just 2 times x. And let's say that we started with an initial guess of 8 and wanted to use the Newton's method to find a root. So there's going to be a root at x is equal to 2, but let's see what happens if we start with an x0 of 8. 8. What I need to do to take one step is given by this, right? So I know that x1 is going to be my x old, so that's going to be x0 minus my function evaluated at x0, so f of x0 divided by the derivative of f evaluated at f0, so that's going to be df of x0. So if I did this, oops, let's define both of those. So if I did this, apparently the next step is going to be 4.25, right? So I can also plot those points. Let's first plot x0 and the y evaluated on that graph, right? So f of x0. So apparently that's going to be my starting point. Then my next point is going to be this. So apparently, if you drew this derivative starting from this point, you would end up here somewhere, and then this is going to be my new guess. Now, now let's pretend that we didn't have this df function. If I wanted to find a root, I could also use the secant method. In that case, my x2 is simply going to be whatever is written here. Right? So I could actually just do this because x1 and x0. So I'll pretend that this was my first point, and this was my second point. And then here I need to multiply sign inst r, but I'm literally just copying this function here. And then it should give me another x2. So apparently it's x2 f of x2. If I started with these 2 points, then the secant method would give me this next point. And then, of course, I could rename my x1s and x2s, right? So this old x1 is going to be my new x0. So the old x1 is going to be my x0. My old x2 is going to be my new x1. And then again, I can find a new x2. So this is now going to be my x0. This is going to be my x1. So I should find some new x2 here. And that's simply going to be this function. I think that this should work. So apparently it's found some new x2 here. And I can also plot this x2. So we see that if we started with these 2 points, then the secant method is going to give me this point. And again, I can continue doing this so that I move closer and closer to a to this root on 2. Okay, so that's how that would work. Okay, so now we can also have a look at what happens if we try to optimize this function. So now I'm going to look at this method, for example. So this is a univariate case, right? So I can look at this univariate example. Again, I'm going to say that my x old is going to be 8. And now my new x1 is going to be 8 minus the derivative evaluated there. So df of x0 minus the second derivative evaluated at x0. So the second derivative here is just the derivative of this. So that's actually just going to be 2 evaluated at x0, but it turns out that that is a constant. So we can have a look at what happens if I ran this function, x1. And I see that in one step, I've already converged to an optimal, right? So that's because this is a second degree polynomial. So it turns out that if you used Newton's method here on a second degree polynomial, you should always converge to a optimal, I think, immediately. But yeah, so that's what you would do if you had a function as well as its derivative and its second derivative. So that's how you would take one step. Yeah, and so as with all of the other methods here, the main thing that you have to understand is where am I? What do I need to take one more step? And then just keep taking steps until some kind of stopping condition is reached. There's really nothing fancy going on.